Nature has already solved the problem of fuel-free operation, and it looks like a moth with no way to consume calories. We are analyzing the metabolic architecture of the Attacus atlas to understand its methods of survival. Its thorax functions as a high-density battery, providing a model for the next generation of autonomous technology. Despite its immense physical scale, this organism operates under a set of biological rules that exclude standard energy intake. Its life cycle challenges existing models of fuel use, demonstrating that a finite energy supply can be used to achieve specific mechanical goals. This chart shows the physical dimensions of the adult. With a wingspan frequently measuring between 250 and 300 millimeters, it is among the largest lepidopterans ever recorded. Examining the head reveals an evolutionary choice. The adult moth possesses only a short vestigial proboscis. This anatomy lacks a functioning digestive tract. The adult insect is physically incapable of processing food. Locked into a fixed energy budget, the moth faces a biological countdown. It has a total adult lifespan of only 1 to 2 weeks. Every movement, particularly the energy-intensive process of flight, is a direct transaction. Energy is spent from a bank that can never be refilled. The adult Attacus atlas functions as a sealed, closed-system machine, existing solely to execute a single terminal mission. To sustain this mission, the organism completes its entire energy acquisition phase during the caterpillar stage. This larval period is a dedicated charging cycle. This builds a foundation of triacylglycerols, or TAG, stored in the fat body as a high-density biological battery. During pupation, it seals itself off, locking energy at maximum capacity and removing physical structures for new energy input. This contrasts with standard human engineering. Most mechanical systems are built around continuous refueling, requiring the weight and complexity of intake valves and processing systems. By front-loading energy, the moth eliminates the weight of a digestive system during the flight phase. It carries exactly the fuel it needs for its lifespan. To move that energy from the fat body to the wings without burning out the system, the moth uses a specific biochemical pathway. Adipokinetic hormones trigger the conversion of stored TAG into diacylglycerol, or DAG, allowing the fuel to enter the transport system. A transport vehicle called ApoLP3 attaches to the DAG, creating a low-density molecular shuttle that moves through the insect's hemolymph. The shuttle delivers the DAG fuel to the flight muscles and releases it, providing power for wing movement. Unlike human transport, this biological shuttle isn't consumed. It returns intact to the fat body to pick up the next payload, repeating the cycle. This reusable, non-destructive transport system achieves a level of metabolic conservation that conventional combustion engines have not yet reached. Beyond the internal fuel, the moth must manage its external propulsion, the 16 square centimeter wings. Pushing that surface area through the air should logically deplete the moth's finite battery in a few hours. Computational fluid dynamics models show that a perfectly rigid wing of this size would generate significant positive drag and negative lift. Flight is only possible because of structural flexibility. The moth uses wing deformation to manipulate air currents, bending and twisting to find lift. This method achieves movement through flexible mechanics, rather than brute mechanical force typical of traditional human aviation. For over a century, human engineering has focused on heavy, rigid aerodynamic structures that rely on constant, high-output propulsion. Modern autonomous technology is shifting toward a finite-fuel approach, drawing directly from the constraints of the Attacus atlas. Engineers are removing refueling ports, intake systems, and internal plumbing to reduce weight. This leads to specialized, disposable drones designed for a single terminal flight. By utilizing a set lifespan, these machines can reach the high power-to-weight ratios found in specialized biological systems. This revolutionary model for autonomous tech combines perfect initial energy charges with reusable internal shuttles and flexible, morphing wings. The life cycle of the Attacus atlas demonstrates how an expiration date acts as a prerequisite for its specific operational capacity. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation, beyond the boundaries of reason, only on TEMBODocs.